So, good evening, and thank you all for coming tonight. I certainly want to thank GDAC, all the members of the board, Tom, Mary, for having me down here. It's always a responsibility to have applause before you say anything, because that means I have to say something that merits applause. I'll try to do that tonight. Happy holiday season to everybody. I'm looking forward to having a good interaction with you tonight. But before I get started, a couple of things you need to know. Well, you don't need to know them, but I'm going to tell them to you anyway. I was born and raised in Pennsylvania, so coming down here is always coming home again to me. I got to show you this. The score was 33-0. It was not our best moment. Now that the ice is broken, okay, some ground rules. I will try to tell you the truth, the whole truth, and nothing but the truth as I know it. One of my favorite quotes, it's common that engineers talk about things like this. So opinion is fine, everybody's entitled to their opinion, but as you know, nobody has an option to alter the facts, and the facts are what science is all about, and science begets knowledge, and my objective tonight, hopefully, is to give you more knowledge than you already have, although I suspect, based on what I've heard from people in GDAC, most of you are very knowledgeable. So for that I apologize. I'm probably going to be going over some old ground. You're going to be hearing things you already heard before, but perhaps I'll say them in a way that further enlightens you or deepens your understanding. Hopefully I'll talk about things that you had not heard before. But I'm going to try to base almost all of what I say tonight on my best understanding of science, technology, and engineering. But I have to warn you that there will come a time towards the end of my talk, somewhere around 11:15, slide number 61, where I will transition, and I will tell you, I'm transitioning from informing you as an engineering educator to trying to influence you as a citizen. So I'm going to give you my opinions, but I'll let you know when there are opinions, and then you can take them for what they're worth, okay? So before that, hopefully science. Some ground rules. I think it's best that we try to preserve the Q&A till afterwards, otherwise we won't get through what I try to do. I'll take questions across the whole field of topics that I've covered, and if there's something I haven't covered that you think you can get something out of me, I'll try there too. So with that as an introduction, anybody else have any suggestions as to what we might do tonight? Let's do this. Okay. So how we're going to do this. Engineers like to outline things. We like to have structure to what we're doing, so you know what I'm going to do, when I'm going to do it. So the first thing I'm going to try to do is, in a very short period of time, perhaps 10 minutes, dispel some of what I think are the principal misunderstandings, the principal myths, untruths, half-truths that are bandied about from across the spectrum, from CEOs of corporations to the opposite. So I'm going to try to do that in a brief period of time so that we all understand what we're really talking about and what the technology, science, and engineering really is. And then we'll dive deeply into various aspects of those technologies, and I'll try to show you how things actually do work and don't work. So that's going to happen first. Then I'm going to show a brief segment from a movie from the gas industry. You've probably all seen it. It's been online for 2 years now. And I'm going to show it for two purposes. One is an animation, which is always better than a still picture, of how drilling and fracking occur in a well. And in doing so, I'll show you some of the accuracies in that movie, but more importantly, I'll also show you some of the inaccuracies. And that will set the table for the actual technologies, what I'll try to describe in the next segment, which is, what do I know about this? When did I know it? So Tom said I've been doing this for 30 years, actually more than that. So it's important that you understand my credentials, my experiences, my life's experiences in this, so that you can weigh the value of what I'm going to tell you tonight. Then, the potential scale of the play. By scale, I mean spatial scale and temporal scale. How many wells can we expect, can you expect in Pennsylvania? Over what period of time? Where are those estimates coming from? What's driving those numbers? Because if we don't understand scale, how big this whole activity is becoming, you can't possibly understand the most important outcome of tonight, and that is risk. Everybody sitting in this room is here for one reason. I guarantee it. You want to walk out of here having a better idea of whether, as this happens in Pennsylvania, you have something to gain or something to lose. That's why you're here. On the gain side, you could possibly financially gain. On the loss side, you could possibly financially lose, or you can have your environment or your health impaired. And what you want to know is, what are the risks? Those things will happen. Some of you will be financial winners. Some of you will be financial losers. Nobody in this room is going to get healthier because of this operation. Some of you might get less healthy. But there's risk in everything. We're talking about high technology industrialization that has a place in our society. So the bottom line is, you ought to walk out of here with a better idea of whether you think, from the point of view of risk, you understand the risks, you can assign numbers to those risks so that you can make informed decisions as to how you want to proceed. And of course, we'll talk about not only the good things about the technology and how it works, but what can go wrong. We're talking about a very complex set of engineering enterprises. Things can go wrong, things have gone wrong, things will continue to go wrong because they're human activities. So we'll talk about what things can go wrong from way down there, from near surface, and from on the surface. That's the way I like to think about things. And finally, this is where I transition from science, engineering, technology, fact, and data to my opinions. And I'll let you know when we get to this part of the talk, and then we can all decide at the end whether it's all been worth it. Okay? So now we know where we're going. Let's go there. Dispelling of myths. Okay. So the most important myth that I want to dispel is the following. Since 1947, over 1.4 million gas and oil wells in the United States have been hydraulically fractured. What's the big fuss about this one? Why is this different? Why is what's happening in the Marcellus different? Is it? And the answer is yes. And I have to explain to you why it is substantially different. What we're talking about is not conventional gas development. We're talking about unconventional gas development. Well, what's in that word? Everything. So I have to tell you why it's unconventional. And I have to tell you that it would be technically and financially inadvisable for an operator to try to produce gas from an unconventional source like the Marcellus if that operator had not acquired relatively recently 4 technologies and combined them. So unconventional gas development from shales is a relatively recent enterprise, fewer than 15 years old, the result of American enterprise that combined 4 separate technologies in a way that unlocked unconventional gas shale. Okay, so this has not been going on since 1947. It's an entirely different beast, and I'm about to show you why. What are the 4 technologies? I'll describe them with pictures and with words. So first, directional drilling. Back in the 80s when we were working on this, we, meaning I with Schlumberger, we called it deviated well bores. But that has certain overtones. So it later became directional drilling. Directional drilling means that you can drill a hole in any direction you want. Not necessarily vertical, not necessarily horizontal, but literally in any direction you want. Not just one curve, but multiple curves. Whatever the technology and the geology let you get away with, you can do it. Well, why is that one of the 4 necessary technologies needed to unlock unconventional gas? I'll use a cartoon you've all seen before from geology.com. It's a cartoon. It's not to scale. Where we're sitting right now, the Marcellus is probably 6,000 to 7,000 feet down. So this is 6,000 or 7,000 feet. But the thickness of the shale layer known as Marcellus is only a few hundred feet. So maybe 10 times the height of this room. So why would you go through the bother of drilling a hole 7,000 or 8,000 feet down and your well is only going to come in contact with your resource for a few hundred feet? That doesn't seem like a good thing to do unless all the gas down there is in one pocket. So if all the gas was right here, stored in one big pocket, all you need is a vertical well to punch through it. That's conventional gas development. But that's not what's down there. The gas that's down there is everywhere in the shale. It's not confined into one pocket, into a graben, into a trap. like it is in sandstones and limestones, but in shale, the gas is relatively uniformly distributed throughout that layer of rock. That direction, that direction, that direction, and that direction. So if you drill a vertical hole and you only expose the well to a few hundred feet, you're only going to get the gas out of a few hundred feet of rock. With directional drilling, you can turn and go in any direction the rock is going. It might be horizontal, it might not be. Whatever direction the geology says the rock is going, that's the direction you go. And you can go a long way. So engineers don't like to use words like tall, short, long, fast. We always try to make sure we know what we're talking about. Long means a mile? 2 miles? What's the record right now? Is there a shale formation anywhere in the world where there are 2 mile laterals? Yes. In Pennsylvania, the record right now is about 7,400 feet, a mile and a half. So what that means is you now have a well that has long exposure to the inventory. The inventory is where you have your product. The product of a gas operator is gas. The inventory is everywhere, therefore you have to go everywhere to get it. Got that? So you can see why directional drilling is important because of the geology. The shale layer is thin, and because of the way nature put the gas in the shale, it's everywhere. Go back to the second technology. High frac fluid volumes. Conventional gas wells typically use less than 100,000 gallons of fracturing fluid. Now, for those of you who don't know anything about fracturing, you might think 100,000 is a big number, but as we proceed tonight, you're going to see 100,000 is a very small number, unless it's the amount of money in your checking account. So high volume in New York State is defined as anything over 300,000 gallons. And as you'll see later in the talk, typically for unconventional shale wells, we're talking millions of gallons of frac fluid. Why? Well, because we can drill through a mile and a half, or 2 miles of shale, we have a really long well. The well could be 3 or 4 miles long. Just to get all that fluid down there, it takes a lot. Fill up a pipe that's only 6 inches in diameter that's 3 miles long still takes a lot of fluid. But you're trying to create recreate many fractures. Show you a picture of what I mean. Okay, up in New York State we have lots of gorges. You've all heard the phrase Ithaca is gorgeous. Or gorges, which one is it? It's both. Okay, if you walk through any of the gorges around Ithaca, you can see exposed shale layers, including black shale layers. So this is a picture from the bottom of a Tegonic Gorge. And this is a black shale layer, and you notice those are natural fractures. They're called joints. The geologists would call them joints. They're really fractures that have occurred because of natural geological processes. You've also heard that shale is impermeable. The industry says, here's another myth, it's impossible for what's down there to get up here because there are many layers of impermeable rock between down there and up here. There's no such thing as impermeability. There's only scales of impermeability. But it is true that the Marcellus rock itself, if I had a piece of Marcellus rock in my hand, say I took a piece right out of the middle of that block, it's relatively impermeable. That means that fluids do not want to flow through it very easily. It's not like the sponge in your kitchen that has all those big holes in it, and all those holes are interconnected. So if you pour water in the top of the sponge, it comes out the bottom. So the holes in the shale are microscopic, and they're not connected. So fluid, liquid or gas, does not want to flow through that rock very easily. In fact, it might take a molecule of gas in the middle of that block years to get to the nearest crack, joint. But since it's been down there for 390 million years, a lot of that gas has gotten to those joints. So most of the readily available gas in the Marcellus is not in the Marcellus. Oh, here goes Ingraffea with those conundrums. Most of the gas in the Marcellus is not in the Marcellus. It's in the joints in the Marcellus, because that's where it wants to go. And that's where it's easy to stay stored for somebody to come and take it away. So another misnomer, another myth, hydraulic fracturing is not fracturing, it's refracturing, because there are already fractures. The purpose of hydraulic fracturing is not to create new fractures, it's to open up the existing fractures. Why? Because that's where the gas is. Got it? Okay, so why do we need high volumes? Well, let's put our imaginary 1.5 mile long lateral, right? Imagine that's 1.5 miles. How many of these joints are we going to intercept if there's a joint every 2 feet? Thousands of them. And how much fluid do we have to put in those joints to open them up for hundreds of feet in each direction? Even though we're only opening those joints, how much? How much are we opening these joints? Are we creating cracks this wide down there? This wide? This wide? A little bit more than the diameter of a grain of sand. But when you've got acres and acres of cracks open the width of a grain of sand, it takes a lot of fluid. So, second technology that had to be invented was the ability to bring to a site high volumes, to store high volumes on a site, and to inject high volumes. That takes a hell of a lot of horsepower. Again, there's one of those engineering words, hell of a. Okay, thousands of horsepower of pumps. This is not your pressure washer for your deck, okay? We're talking thousands of horsepower needed to pump those high frac fluid volumes down 2 or 3 miles along a pipe that ultimately is only the casing, the production casing, the stuff that's down there on the lateral through which the gas is going to flow back. What's the diameter of that pipe? 4 to 6 inches. Okay, so here we go with my favorite analogy. Garden hose. You connect your garden hose to your faucet. Is the rate at which the water comes out the end of the garden hose the same as the rate at which it comes out of the faucet? Yes or no? No. If you make your hose long enough, what comes out the other end? Nothing. Why? Friction. So there's pressure loss and flow loss as you're trying to force a fluid through a hose, just like there is as you're trying to force a large volume of fluid, millions of gallons, through a 6-inch diameter pipe over 3 miles at what pressure?
6,000 pounds per square inch.
Or more, depends upon the geology and the depth, up to 10,000 pounds per square inch. So you need a lot of horsepower to do that. Okay. I'll show you a picture later on where there's 40,000 aggregate horsepower involved in one frac job. Okay. But now we've invented another problem. We took these two technologies, directional drilling gets us long exposure, ability to inject high volumes of fluid over long distances through small diameter pipes in a relatively brief period of time at very high pressures. Friction. We got to make the water slick. That's where the slick water name comes from. You have to lubricate the water, which is a concept that most people think is crazy. Isn't water slippery? It is when it's frozen. Okay? Water is inherently slippery, but it's not slippery enough. Same thing with the water going through your garden hose. So some chemists working for gas companies had to invent chemicals they could add to water that effectively reduce the friction of the water passing through the casing, and in fact reduces the friction between the water molecules themselves. It's like lubricating your automobile engine, right? So that was the next technology. You can't get all that high fluid volume at the high pressure down that long pipe of small diameter in a relatively short period of time unless you reduce friction, and that's slick water. Okay. Fourth technology, multi-well pads. A pad, as you know, is an area where there is drilling and fracking going on. A number of acres that have been cleared, industrialized. Conventional wells typically have one well per pad. Why? I just told you the answer. It's all in the geology and how the gas is stored. Why do you only need one well on a pad? Because it's either down there or it's not. It makes no sense to drill one well here and then move 10 feet away and drill another one. You might want to move a mile away because you missed. You got a dry hole, right? You thought there was gas down there. You didn't get it. But where's the gas in the Marcellus? Everywhere. So if you're going to go through the effort of clearing an area and setting up shop with heavy industrial activity where you're going to drill a well in that direction, why not drill another one in that direction? And then move 17 feet and drill another one in that direction and another one in that direction. And then move 17 feet, excuse me, I'm getting close here. And do that until economically you say, well, I've gotten the most out of this one pad, I'll move on to another pad. So the idea of drilling more than one well from a pad, again, is dictated by the geology, the gas is everywhere, and dictated by economics, and controlled by whom? Gas companies, and DEP, and who's leasing the land? Y'all. right? So if a gas company wants to come and put a pad here and drill 8 or 9 wells that way, 8 or 9 wells that way, that's going to be a pretty big pad, and it's going to take up a lot of land underground. It's going to drain a large area, square miles. And they have to have permission from landowners to do that. Or they have to not get permission and still do it, depending upon the laws of the land. It depends upon whether you're in New York State or Pennsylvania. Okay? So, those 4 technologies are recent, relatively recent. None of those technologies was around in 1947, when hydrofracking first became available. The vast majority of the gas and oil wells that have been fracked in Pennsylvania were fracked conventionally. All the gas and oil wells in New York were fracked conventionally. Okay. So how old are these technologies? This is data from the New York State Supplemental Generic Environmental Impact Statement. Okay? This is a table, so it's not mine. Let's see. Slick water fracturing fluids introduced 1996. That's not 1947. That's a myth. We don't frack Marcellus wells with traditional fracking materials. Gel fracking, gel gas fracking, sometimes hybrid fracking, yes, but usually slick water. Not always, but most of the time. Multi-stage slick water fracturing of horizontal wells. Oh, combined slick water, high volume, in a horizontal well. 2002, down into Barnett. The first hydraulic fracturing of the Marcellus Shale, Pennsylvania, 2003, Washington County. And finally, use of multi-well pads and cluster drilling, Pennsylvania, 2007. So this is all relatively recent. It's not, a myth is that the industry will say, we've been doing this for millions of times, over 60 years, what's the hubbub? The hubbub is it's relatively new technology. You're still inventing it. You're still evolving it. It's still an industrial process that has yet to reach a steady state operating procedure because every well is going to be different and every formation is going to be different, and capital and leasing control what they do. This is going to be a constantly evolving technology. This will never be a technology in which a building goes into your zone, your industrial zone, and you build toasters. Same thing over and over and over again. It's constantly going to evolve because that's what Mother Nature is going to force the industry to do. All these were natural evolutions in response to geology and gas distribution. Got it? Now we know what we're talking about. Unconventional gas development. Large volumes. Very large volumes. 100 times more than previously used. Multi-well pads. Horizontal drilling. Necessary to add different chemicals to the fracturing fluid than we've used before because of requirements of that massive hydraulic fracturing process. Okay. So that's what the hubbub is about. Now we're saying, you, I, maybe, we're all saying, well, is that new technology safe enough for us? Are the risks acceptable? Because it's a new technology. All right. Let's see if what I just said is academic balderdash, poppycock, Ivy League professor comes down and talks to you and blows smoke. No, I don't think so. So let's go to the industry itself and put to the test whether those 4 technologies have been combined any place and are being used. Well, they're certainly being used in Pennsylvania, but I think you'd like to know, given that in Pennsylvania they've only been in use for 3 years, what's in store? What's happened places where it's been used for 10 years? About as old as it is. So we're going to do an experiment. This is a map of the Dallas-Fort Worth, Texas airport. So imagine that one gas company, in this case it happened to be Chesapeake, one gas company got control of a large area. That is, they convinced all the landowners in that large area to work exclusively with them. Can happen. Obviously, the companies are in competition with each other. There are 74 operators producing gas in Pennsylvania right now, and they're not all good friends. Okay? But let's suppose that one company could go into an area and convince all the landowners in that area, work with us exclusively. Well, that's what happened here. So Chesapeake made a presentation to the Dallas-Fort Worth City Council and said, you give us the right to drill on your property at the Dallas-Fort Worth Airport, and we'll make you rich. And they did. And so what did they do? Every one of these lines is a well. Every one of these red dots is a pad. So there's 18,000 acres, there's 53 pads, and they drilled everywhere they could possibly drill on that airport site, except on the runways, in the parking lots. Now they drill in the parking lots and in the terminal. And in doing so, they were able to capture most of the gas stored in the Barnett, in this case, under that entire area. So you see what the difference is here? If this were conventional gas, there might have been one pocket of gas right here. They drilled a well, they hit it. And then they went somewhere over here or over there or over there. But here the gas is everywhere. Everywhere you put wells, you get gas. Therefore, put wells everywhere. Everywhere you can. So what controls this? The geology, the distribution of the gas, and the leasing arrangements. And that's what's controlling what's going on in Pennsylvania. I told you a few minutes ago, I'm going to show you what the technology is evolving towards, because I'm going to repeat this again and again tonight. The technology is not steady state. There is no standard operating procedure. You don't find a book right now that says, how do you develop an unconventional gas well in Marcellus in central Pennsylvania? That book is being written. Chapter by chapter, every well adds another couple pages to each chapter. But the experiments, where the industry is looking to see the experiences of the future. How can we make this operation work better? How do we get more gas out for fewer dollars down? That's the bottom line. From a corporate point of view, more gas out, fewer dollars down, higher profits. That's good. This used to be the world's largest frac job. In April of 2010. This year, in April, this was announced as the world's largest frac job. It's in northeastern British Columbia, where there's a big shale field, and it's being drilled substantially. Gas is going to be piped to the west coast of Canada, liquefied, sent by ship across the Pacific to sell to the Far East. Good business. 16 wells on that site. Okay, so I'll give you some statistics. Here's that pad right here. There's 8 wells going northwest and 8 wells going southeast. Why do you suppose some of the wells are going northwest and some of them are going southeast? Why didn't they go north-south? Natural fractures. You want those wells to cross the most natural fractures because that optimizes your production. Okay, so that tells you the direction they're going. What controls how far they drill those laterals? Lease controls and economics. It costs a lot more money to drill a 2-mile lateral than it does to drill a 1-mile lateral, and if you're not producing very much gas from that lateral, you might choose not to go 2 miles. Or maybe you choose to go 2 miles to produce more gas. It's complex formulas. But look at the numbers. To get those 16 wells fracked, every one of those dots is a frac job. You don't fracture the entire lateral at one time. You fracture in intervals, as we'll see in the movie in a few minutes. So there were 274 individual frac jobs involving 111 million pounds of sand, 220 million gallons of water. Okay. That was April of this year. November of this year in Kana, that was Apache, by the way. In November of this year, Kana bragged on its website and to its shareholders that they now had the largest frac job in the world. Also northeastern British Columbia. This is a square kilometer. Here's the frac water holding pond. Here's the flowback holding pond. 417 million gallons of water, 78,000 tons of sand, 8 million gallons of fracking chemicals, 500 frac intervals, 2-mile-long laterals, and 40,000 horsepower of pumps. What's another difference between conventional gas and unconventional gas development? You've heard it before. It's heavy industrialization. It took 111 days to complete that frac job. It's a third of a year. Okay. 40,000 horsepower running 24/7 during that 111 days. That's a lot of noise and a lot of air and light pollution. And how do you get 74,000 tons of sand to a place? It's not a sand ferry. It doesn't come by helicopter. It comes by truck. You count the number of truck trips. How do you get 417 million gallons of water to that lake? Truck. Okay, or if you're lucky, if you have another pad over here, maybe that lake is serving 2 of them and you got a pipeline between them, but somewhere you got to go get the water to put there. Okay. So the point I'm making here is another major difference between conventional and unconventional is the amount of time on the site and the industrialization activity on the site and the attendant risks. The risks are higher. I'll make that point again and again tonight. No industrial activity, even building a toaster, is risk-free. What I'm saying is in going from conventional to unconventional, because you're drastically increasing the industrial activity, the quantities of materials that have to come to the site, and the quantities of materials that have to be removed from the site, the risks go up. You have to answer the question, is it worth it? So, summarize so far. I'll ask you the question, why is this modern kind of thing, slick water, high volume fracking from long laterals, a higher risk to the environment and human health? Simple reasons. Requires much higher well density. I just showed you. Your gas is everywhere, put a well everywhere you can. Many wells per square mile. Requires much more industrial development over large areas, over a large period of time. Requires much higher volumes of fracking fluid, millions of gallons per well. Produces much higher volumes of waste fluids and solids containing hazardous materials. What's down there is hazardous material. It's been stored safely down there for over 300 million years. Okay. The methane itself is only hazardous if you light it or confine it and set it off. You can drink it, you can breathe it, it ain't going to kill you. But the other stuff that's down there is not good for the human health. Heavy metals, naturally occurring radioactive materials, chlorides, BTEX materials, and the liquid phases of the natural gas. Produces much higher volumes of those things, produces much higher volumes of fugitive emissions of methane. Come to that later. Those of you who are concerned about global greenhouse warming and climate change, that's the single most important reason to think twice about drastically increasing the production of natural gas. If you don't want to think that, then ignore that and concentrate on the first couple. So what does this all mean from a mathematical point of view, a risk assessment point of view? As the number of wells and the volumes of waste increase, the probability of accidental releases of hazardous materials into the air and into the groundwater increases. That's patently obvious to everybody. Every time, how many times do you have to roll 2 die before snake eyes comes up? Well, the more times you roll, the more probable the snake eyes are going to be. So if you have 1,000 conventional wells, low volume, low industrialization, low waste, or you have 400,000 unconventional wells in the Marcellus, the odds go up that bad things will happen. Are you willing to accept the risk? Is the reward worth the risk? Cumulative effects on air and water from these accidental releases and from purposeful emissions into the atmosphere and releases into groundwater are unknown. Who would be crazy enough to purposefully emit into the air or into the groundwater things that we know to be hazardous? That's not a rhetorical question. So as you well know, the oil and gas industry has a number of exemptions that make them different from all other industrial activities in this country, and that they can do certain things according to federal regulations that other industries cannot, including purposeful emissions and discharges. Okay. We don't know the cumulative effects of those. So if there are going to be, as the industry estimates, over a 30 to 40 year period, 400,000 wells, not in Pennsylvania, but over the entire Marcellus, what can we say life will be like in that area 20 years from now? Do you know? I don't know. Has anybody predicted that? Has anybody done a concerted science-based study to say, well, if the probability of there being this kind of accident is 1 in 100, and we have 400,000 wells, and if the probability of this accident is 1 in 200, and we have 400,000 wells, then add up all those, it is rocket science, because somebody has to do the basic research to answer those questions, and that research has not been done. And you guys in Pennsylvania opened the damn barn door before you were supposed to. So now you're hoping that the studies being done in New York State and the studies being done at the federal level are going to come back and tell the industry, you need to develop better practices. And you need to quantify the risks and be transparent and honest with the people that you affect and tell them what's likely to be happening to them 5, 10, 15, 20 years down the road. You're 3 years into a 30 to 40 to 50 year development. There's 2,000 Marcellus wells in Pennsylvania, more or less. And there are going to be a couple 100,000. So what can you tell me at this point that things are going to be like? You can't tell me, the industry can't tell me. Can we predict with some degree of acceptable reliability? Yes, if we do our homework. Increased production and burning of natural gas and its liquid companions, ethane, propane, butane, increases emission of greenhouse gases. Another myth. Natural gas is a clean fossil fuel. Okay, I'm sorry, this is on the verge between my telling you about facts and data and my offering my opinion. What do we mean by clean? Do we mean that if you burn an equivalent quantity or BTU amount of coal or petroleum or natural gas, there's less CO2 coming out of the natural gas burning? Yes, that's perfectly true. From that point of view, that's a true statement. Burning natural gas is cleaner than burning petroleum or burning coal, BTU per BTU. But that's a rather narrow perspective. We're talking about global greenhouse gas impact, which means you have to look at the entire life cycle of getting to the gas, bringing the gas to the surface, processing the gas, transporting the gas, and then burning the gas. And along the way, it leaks. So somewhere between 2 and 6% of all the natural gas produced in the US from conventional and unconventional sources leaks into the atmosphere. So, isn't methane a greenhouse gas? Yes. Is it more potent or less potent than carbon dioxide as a greenhouse gas? Much more potent, somewhere between 20 and 100 times, depending upon how long you're willing to allow it to be resident in the atmosphere. So a relatively small percentage, 2%, of a really big number, 23 trillion cubic feet of natural gas was consumed in the United States last year. So 2%, 3%, 4% of 23 trillion cubic feet, you start talking about a lot of natural gas, and that natural gas is 20 to 100 times more powerful than carbon dioxide as a greenhouse gas. So you do the numbers. Okay, so myths. The technique of drilling and fracturing. So I repeat, I'm going to show you snippets of a movie. A couple reasons. Seeing something in action is better than just seeing a cartoon. A lot of what's in the movie is perfectly accurate, and it gives you a better perspective of the actual drilling and fracturing process. Some of the stuff in the movie is inaccurate, and I'll try to point those things out. Notice that while that's happening, what we have is what's called an open hole situation. There is no cement, there's no casing, you only have the drill string, which is drilling a hole in the rock. And initially that hole is maybe 18 inches in diameter, and then you go down and it goes down to 12 inches in diameter, and then down to maybe 8 inches in diameter, and ultimately something like 5 or 6 inches in diameter. But while the drilling is going on, you have open hole. So that drill string is going to, in this movie, pass through the water table in a minute. Okay, and when it does, you've got to imagine, let's see, in that there's either compressed air or drilling mud, and I'm drilling through the water table, and there's nothing between the water table and the drilling mud or compressed air. Oops, but that's always true. It doesn't matter whether you're drilling a water well, a conventional gas well, an oil well, or an unconventional gas well. While you're drilling through the water table, you are poking around in your water. And you're liable to have whatever is in that hole get into the water table. So that's the common problem that we see every time you drill a well. People who are downstream of where you're drilling are liable to get muddy water in their well. And if they're using if they're using drilling mud, which they sometimes do instead of compressed air, then elements from that drilling mud will also go into the groundwater. That's unavoidable. No one has ever invented a way of drilling through the water table without drilling through the water table. Okay? So it's a problem. It's always existed. It will always exist. It's important to understand here that when you drill the hole, the diameter of the hole you drill has to be larger than the diameter of the casing. It's kind of hard to push a steel pipe through a hole whose diameter is roughly the same as the steel pipe. That hole has to be bigger, usually 3 inches in diameter, which means this cement is on the order of an inch thick. So the so-called annulus that you've heard so much about, the cement problems, the bond problems between the cement and the casing, or the methane or frac fluid migration through the cement, it's important you understand the scale of things here. So if this is 8 inches of steel diameter, okay, that's 1 inch of cement. And that cement has to completely fill that annulus, otherwise you have the possibility of migration. That's a problem that's been around since this drilling process was invented back in the early 1900s. And that is a miracle. This is the directional drilling miracle I told you about. How do you drill a hole that doesn't go? How many people here are carpenters? Would you like to have the opportunity to drill a hole while you're making furniture that goes around a corner? Okay. And measuring while drilling, this is the electronic revolution. How do they know where that is? It's 5,000, 6,000, 7,000 feet down. How do they know where it is? No, because satellite can't communicate with what's down there. It's all electromagnetic communication through the rock itself. The rock is very conductive to certain wavelengths of electromagnetic radiation. So if you were ever in a doghouse, no. Am I talking to the husbands and fathers here? Or the doghouse is the place on the drilling rig where the guy is controlling this process, and he's got an LCD panel screen, and he can actually, this is what he sees. It doesn't look like a cartoon. And he's getting constant signals from the electronic device down here that goes through the rock and tells him exactly where that is to within a few inches. And then he can control the speed and the angle that motor has. The drill string is not turning anymore. The only thing that's turning is what's down here. There's a motor down there that's being driven by the pump fluid pressure. It's a hydraulically driven motor that turns just this part. This is just following along for the ride. So it's the idea that you're turning the whole thing. No, you're only turning the stuff on the end, and that's why you can turn. At that time, the drilling is completed. When you read on the DEP website that a well has been drilled in this county, that's what they mean. That part of the process is done. Right? It does not necessarily mean that Schlumberger or Halliburton are now going to show up, or BJ Services, and do the next step, which is the fracturing. In fact, I heard recently that a large number of the wells that have been drilled in Pennsylvania have not yet been fractured. Well, why not? Gas price is too low. No infrastructure to process it, no infrastructure, no gathering lines to take it to your transmission lines. But on the other hand, and no place to put the wastewaters, and on the other hand, if you do the drilling, what have you done to the lease? You've executed it, right? You've locked up the lease. So typically, on the pads I've been on in Pennsylvania, you'll see a vertical well that was used as an exploratory well to make sure everything was hunky-dory, and the computer models that they're going to use to predict how all this is going to go on are fine-tuned, and then they'll come in and drill 1 or 2 horizontal wells and go on someplace else and shut those wells in. They'll come back later to do the fracturing to start producing the gas. So it's not necessary that they immediately go to this next step. Last part of the movie I'm going to show you, because this is the part that irritates me a lot, because this is right in my wheelhouse. This is what I did for a living for Schlumberger for 20 years. These dead trees in winter, that's artist license. That's not what's going on. What's going on is what they don't show in this movie is that the shale is already fractured. You saw the images of the fractures? And what they're trying to do is force the fluid into those existing fractures. There is some additional fracturing that goes on because they can never perfectly line up every one of those perforations with an existing fracture. They can't do that. So some fracturing goes on, but as soon as the fracturing that does happen meets a joint, that's a weak plane, and that's where the fluid's going to go. So you don't get this shattering effect like a big explosive going off down there. So that's not quite right. It's also not quite right that all this happens to end. It might not. It's a very complex mechanics problem. I have a PhD student who's going to be defending her thesis next Monday, and it's exactly on what happens when a crack approaches a bimaterial interface. Ooh, heavy words. Material A, material B. This might be a sandstone, a shale. This is probably a sandstone or a limestone. They have different properties, and the joints don't necessarily line up. And this is the interface between them. So when a crack gets there, it has a bunch of decisions to make. It can stop, or it can go on through, or it can deviate and deflect and then go on through. All those wonderful things can happen. Those are things that do happen. So the movie is not quite complete. But you get the idea by now? Okay, this is how it works. All right. So now that you've seen the cartoon and you've seen a still cartoon and a movie cartoon, I'm going to show you the real thing. Okay. So now we're in what did I know and when did I know it? Contrary to what you think right now, I'm not as young as I used to be and look, but way, way back when I had all black hair and a lot of it, I went on my first sabbatical. That's the boondoggles that professors get every 6 years, you know. I wasn't boondoggling, I went to work in the unconventional gas program at the Lawrence Livermore National Laboratory, one of the weapons labs out in California. And there was an unconventional gas program funded by the Department of Energy. So we've known for a long time that there was gas in the shales out here. Okay? And we were working on it back then. So I'm going to show you some images from the research and development I was doing there for a couple of reasons. One, to show you that the problems we're facing today are old problems, not new. The industry has known about them for 25 or more years, and they're still problems. They're gradually being addressed, gradually being solved, but they're not solved problems yet. That's my point. Okay. Wrote a bunch of papers when I was out there. Here's one from 1987. This is extracted from that paper. Considerable quantities of natural gas are locked tightly into the eastern Devonian shales. In those shales, the gas is mostly drained from the natural fractures, which tend to be vertical and spaced a few meters apart. To recover the gas, it is necessary to stimulate the rock reservoirs. That's using hydraulic fracturing. And rock reservoirs already contain natural fractures, and this makes it difficult to predict the effects of induced fracturing. So we set out on a research program to try to understand what those difficulties were and to try to quantify them and see if we could use computer simulation and knowledge of the rock to figure out how best to conquer those problems. Okay. How many people here have ever done finite element analysis? Okay, how many people here have ever used a supercomputer? How many people have ever done computer simulation of complex fracturing processes? All right, I'm really proud of this picture. It's from a 1987 paper, and believe it or not, the computer we used to do the analysis I'm going to describe was at that time the single most powerful computer in the world. It's about as powerful as the computer in my cell phone right now. But anyway, here's the picture. Here's a well bore, right? Here's the casing. Here's the cement. This is the rock. Every one of those lines is a joint, a pre-existing fracture. And we asked the computer, what happens if we inject a certain amount of fluid at this point through a perforation? And I'll show you a picture of a perforation in a minute. It goes through the cement, fractures the rock, gets into the first joint, and it has a decision to make. Do I go left or do I go right? Well, depends. Depends upon the pressures and stresses in the rock, depends upon the characteristics, the flow characteristics of the joint, the permeability of the rock. And so the computer model says, well, it all went this way, but when it got here, this is Main Street and Elm. It has to decide whether to go left, right, or straight, and some of it went that way, so you got the point. What we have is a network of flow fields. It's like a traffic pattern, right? If 100 cars leave this street at this time, where do they wind up? When they all have opportunities to make left turns, right turns, or go straight. The problem here is that this wound up being an unpredictable problem. We concluded in this paper that it's nonlinear chaos. What that means, for those of you who don't know, wait a minute, you told me these people all, no? They don't know? Okay, a characteristic of a nonlinear chaotic problem is this. A slight change in any of the conditions in the problem results in a big change in the answer. That's not a good position to be in. It makes your computer models virtually useless. They're fun, and you write papers about them, but they're not practical. So we couldn't use this computer model to tell Schlumberger where the fluid was going to go. And that's generally true. Okay. Fast forward 5 years, still working for Schlumberger, but now we're doing actual physical testing. Schlumberger had a computer model that would predict how every one of those perforations, boom, remember those little perforations you saw in a movie? Each one of those perforations spawns a crack. And Schlumberger had a computer model that said the cracks should start at this location, at this time, and take this shape and propagate this fast. Let's see how good the computer model is. That's called validation. It's a very important concept in engineering. Anybody can write down an engineering model or theory, and it's worth nothing unless it can reproduce what you can see. That's called the validation process. So it's always necessary to do physical experiments to show that your computer models have merit. So we drilled a hole just like the movie said. We put a casing in it, steel pipe. We cemented the casing. We perforated the casing in the cement and the rock, and then we injected colored fluid as pressurizing hydraulic fracturing fluid to see how the cracks evolved over time. So here you go. There aren't very many people who have ever seen these things. We broke open the rock when we were done. So we broke open this big piece. And here's the casing. This gray area is the cement. Okay. These pink colored areas are fractures, natural hydraulic fractures. That hole is a perforation. Here's another one here. Here's a perforation in the cement. And there's the overall picture, and what we found out was that the computer model said that the cracks should all be semicircular or elliptical, and they should all propagate at the same rate, and we should have a symmetric result, and we didn't. But that's because we're working in a natural material, where there are variations in the properties point by point. That wasn't man-made sandstone, it was natural sandstone. So even though we could control in a laboratory all the pressures that we were applying to that block, we were squeezing it in 3 directions with the same stresses that would exist downhole. We still didn't get results that perfectly matched the computer models. Close. Okay, so computer models say that, and that's what we got. Reasonable. But that's just to show you that I work with Schlumberger. Okay, Schlumberger is still working on the same problem. I'm really proud of some of my students who went to work for Schlumberger and Exxon, and one of them once got the cover of a magazine which is very famous. It's called the Journal of Petroleum Technology. If you're anybody in the oil and gas industry, you want to get published in this journal, just so you know. Okay. So I'm not bragging that we got the cover, although that's quite an accomplishment in 1989. What was funny to me and ironic today and relevant to you as residents of Pennsylvania who hear things about methane migration and frac fluid migration is that that's not a new problem. So when I went to scan this cover, I put this magazine in my scanner, and before I closed the scanner, I looked at the back cover. And I'm going to show you what the back cover is. It's a full-page ad from Schlumberger. Gas migration control, a comprehensive approach. Here's your casing, here's your cement. If you got migration through the cement or along the cement bond line, you call Schlumberger, and they bring out the golden fingers. And they squeeze that cement shut so that the migration is cut off. How's that for humor? Pretty sick, huh? Anyway, the point I'm making here is this is an old problem, and it will never go away. It is impossible to guarantee in any well, whether it's a water well, conventional gas well, oil well, that your cement job is ever going to be perfect. There's just too many complexities involved. Witness what happened in the Gulf of Mexico this summer. That's a multi-billion-dollar well, and they fouled it up big time because they had a faulty cement job for many reasons. Okay, so that's 1984, 1989. You might be thinking Ingraffea is getting kind of long in the tooth. Maybe he's been out of it too long, and by now they've solved all these problems. I want to convince you that they haven't, but they're still working hard. So here are a couple quotes from papers. Here's a paper from 2008 by this is the Society of Petroleum Engineers. This is a well-known guy who works for a well-known company. This is from his paper. I'll let you read it. The point he's making here is after 60 years since 1947, the invention of hydraulic fracturing, we still don't really know exactly how to control everything or predict everything, but that's to be expected. Moving fast forward to 2009, another well-known oil and gas industry expert. Although our computing tools have improved, the supercomputers are a lot faster now. And if you ever go to a frac site, has anybody here ever been on a frac job? Okay. You'll notice that there's always going to be one van over in the corner, and inside that van are a bunch of computers and a bunch of people with MS and PhDs. And those computers are connected by satellite connection to Houston, where they have the supercomputers running, and they are running real-time computer simulations of the frac job as they're fracking. That's called prognosis, well prognosis. The idea is to predict what's actually happening down there, and by monitoring what you can at the surface, pressure, flow rate, You figure out whether what your computer model said should happen is actually happening. Okay. So after computing tools are improved as an industry, we remain incapable of fully describing the complexity of fracture, reservoir, and fluid flow regimes. So the point I'm making here is that, I'm making it over and over again, beating the proverbial dead horse, we don't know everything. The industry doesn't have complete control over what they're doing. They're working in a natural environment that is not inside of a building in an industrial zone. They're working thousands of feet underground where they can't see what they're doing, hear what they're doing, taste what they're doing, touch what they're doing, or smell what they're doing. They rely on models that are imperfect. The models are imperfect, and the information they feed into the models is imperfect. Will it get better? Yeah, they get smarter. All right. How big an activity is this going to be and why? We're talking quantities of gas, quantities of money, number of wells, number of pads. What impact can you expect over the next 10, 20, 30 years in Pennsylvania? In your county, you have, I think, 14 permits and 2 wells drilled so far. Okay. So be prepared. This year, through November, 1,368 Marcellus wells drilled. Is the rate increasing? Well, yes. In 2008, there were 195 drilled. In 2009, there were 768 drilled. By this year, we will have doubled that. And the industry articles that I read, if capital permits it, and the price of gas goes back up, you'll see something like 3,000 wells per year being drilled and maybe completed in Pennsylvania. So that's the temporal impact. Something between 2,000 and 3,000 wells per year over the whole state. Closer to home, you got 2 wells that were drilled in your county, north and west of here. Why? Why all these wells? There must be something down there the gas companies want. Sure, gas. Where is it? Everywhere in the Marcellus. How do we get it? Drill as many wells as you can. How many wells can you drill? Depends upon what the people who are leasing your land say you can do, and depends upon how much capital you can bring to the job. Average cost of drilling and completing a Marcellus well in Pennsylvania is $4.5 million. Okay, so if they drilled 1,300 wells this year, and each one costs $4.5 million, how much capital is that? We're talking $1 billion, and the companies don't have that sitting in their back pockets. That's go to Wall Street and beg. You got to borrow to get that capital here. So somebody has to make a judgment in the front office. Are we going to make a profit? It's going to cost us $4.5 million to drill that well. We got to go borrow that money, got to pay the interest on it. Are we going to make a profit? Depends upon how much gas we can get out of a well. Okay. So what number are we looking at here? This is the total amount of gas that was consumed, natural gas, in the United States last year, 23 trillion cubic feet. So it will be worthwhile as a natural resource to continue to develop the Marcellus if we can produce safely enough for everybody in the room, safely enough if we can produce an amount of gas that's significant compared to that number. Okay. All right, so how are we going to do that? Well, this guy did it. It's a colleague of mine, Terry Engelder, professor at Penn State. Anybody know him? Okay. Oh, come on. My co-author. Okay, I'll take it. Boo. So he's the father of the Marcellus. He's written more papers and books and book chapters on Eastern Devonian shales and joint systems than anybody else. And he did an analysis, which I'm going to go through here for a minute, and show how he is able to predict, calculate, based on modeling, not on experience, but on models, how much gas could be produced from Pennsylvania, from how many wells, over what period of time. And if you don't have that information and you're the CEO of Chesapeake, you're putting your shareholders at risk. You got to be able to do those calculations. Is this going to be worthwhile from a financial point of view? From a landowner's point of view, how many people here are willing to admit that they've leased? Okay. From a landowner's point of view, you need these numbers that I'm about to show you. All right, graphs. You're all experts in graphs. Horizontal axis is age of a well. Vertical axis is the amount of gas per day being produced from that well. This is data from Chesapeake for an average Marcellus well that Chesapeake developed in Pennsylvania. This is information they send to their shareholders. Okay? This is called a decline curve. Why do you think it's called a decline curve? It is a natural characteristic of unconventional gas wells and shales to have a rapid decline in production rate. Why? You know the answer. I told you already. Because most of the gas that you can easily get is already in the cracks that you're trying to hydraulically fracture and reopen so that that gas can quickly flow back to your casing and to the surface. Thereafter, you have to wait for the gas that's trapped inside the rock to make its way to those fractures that you've propped open, and that takes time. So a lot of gas comes out the first day in the first year, but this is day one. By the end of year one, you've reduced the rate of production by a factor of 3. Okay? So, but those of you who know calculus say, well, if we fit a computer model or a mathematical model to that curve, right, it's an exponential. Yeah, remember those things? Admit it. If we integrate an exponential, we get this. This is the cumulative production, the total amount of gas that will come out of that well. So if we extrapolate that curve, you might remember this, these wells are only 2 or 3 years old, so we only have data here. The rest of it is a guess. So we're really going to be guessing what's happening out here at year 15, year 20, year 30, year 40, year 50. But if you were going to take those guesses, this well should produce in its lifetime a very important number, 4.2 billion cubic feet of gas. So if you're a landowner and you leased, and you have this well on your land, the gas company should have told you at this point, they should have given you this curve and said, we expect that that well on your property will produce this many billions of cubic feet over its lifetime. If they haven't, you're an idiot. You didn't ask. You should have. It's your right to know. It's how they're basing their profit picture. They should be using that, giving you that information so you can make an informed decision as to whether it's worthwhile from a financial, health, and hazard point of view for you to take the money. Okay, 4.2 billion cubic feet. How much is that worth?
About $16 billion at current gas prices.
$16 million at current gas prices, roughly $4.25 per thousand cubic feet. So that well, if this model is correct and using current prices, would produce $16 million worth of gas over its lifetime. But, as I said before, it costs $4.5 million to drill the well. Take that off the top. Now you're down to $12 million. There's $1.28 per thousand finding costs. That's all the cost that leads up to your getting to the well, drilling the well, producing the well. Then there's processing costs because you got to dehumidify the gas, and if you're in southwestern Pennsylvania, you got to get all the other crud out of the gas. So that's another 5, 10, 15, 20 cents per thousand cubic feet. And guess what? You have to pay royalties and bonuses to the people who own the land on this, in which this gas well sits. So if you're paying a 20% royalty on, are you paying 20% on 12 million, or are you paying 20% on 12 million after 300% of recovery costs? What does your lease say? Are all leases the same? Have you negotiated a good lease? Should you have had this information in front of you when you negotiated your lease? Did the company give you this information? Maybe, maybe not. Okay, the point is, at $4 a thousand cubic feet, they're still going to make some money on this well, if all this modeling is correct. It's a model. It's not reality. The oldest producing Marcellus well in the state of Pennsylvania is about right here. Everything after that is pure speculation. So be careful. All right, so if each well were to produce something like 4.2 billion cubic feet over its lifetime, how many wells would it take to get, say, 70% of the gas out of Pennsylvania? And then how much would it be worth? Those are all very easy calculations to do once you have those numbers. So let me show you the numbers. Professor Engelder did this. Pennsylvania, 25 counties overlying the Marcellus, 21,000 square miles. All good engineers and scientists like Professor Engelder will never say anything is true. They always talk in terms of probabilities. So this P50 means there's a 50% probability that I'm right. There's a 50% probability I'm wrong. 50-50. He says there's a 50% probability that my model says that over 5 years, those 25 counties would produce 89 trillion cubic feet of natural gas, which is 3 times the US consumption per year. So in 5 years, Pennsylvania could conceivably produce 3 years of natural gas supply for the entire United States if the model is correct. But you have to read the fine print too. Fine print's important. For these numbers to be used, you have to read the fine print, which says this assumes that 70% of every square mile in each of these counties gets drilled. And each square mile gets drilled with 8 wells. Remember the picture of the Dallas-Fort Worth Airport? Okay, so if you want that much gas, you got to drill 20,000 times 0.7 is 14,000 times 8. 8 times 14 is 112,000 wells in 5 years. Can Pennsylvania drill 112,000 wells in 5 years? I just showed you data. They can barely get 2,000 wells per year. So what's the probability that in 5 years Pennsylvania can solve the nation's natural gas problem?
No.
Another myth. I'm not saying the gas isn't there. What I'm talking about now is temporal intensity. You can't get that much gas out in that period of time because there's not enough capital in the world to bring enough big rigs and frac jobs to the state of Pennsylvania, and there aren't enough intelligent, educated well workers to drill 112,000 wells in 5 years. Okay? So these are interesting numbers, but you got to take them with a grain of salt. Thank you. You can project 50 years, and no one knows if the Marcellus well will produce for 50 years. The oldest Marcellus well is 4.5 years old. So maybe they'll produce economically for 10 years, 20 years, 30 years, we don't know. But if you take the model of Professor Engelder, over 50 years, Pennsylvania, now with all 42 counties producing, 32,000 square miles multiplied by 0.7, 7 times point, that's 21,000, 21,000 times 8, it's 170,000 wells. Okay? So over 50 years, can Pennsylvania drill 170,000 wells? Yeah. That's what, 2,000, 2,500 wells per year. You're almost at that rate now. So it would take 50 years to drill that many wells, and then there's a 50% probability that over 50 years you would produce 300 trillion cubic feet of gas if you drill 70% of each county at 8 wells per square mile. So now you're talking 10 years supply, 15 years supply of the United States over a 50-year period. Not negligible, but be careful about the hyperbole and the advertisements that we're going to solve the Mideast war crisis and we're going to be totally energy independent. Okay. All right, what's it going to look like around here in 50 years? It's not going to look like that. This is not an unconventional shale gas development. It really bothers me when people show this picture and say, here's New York State in 20 years, or Pennsylvania in 20 years. It's not going to look like that. This is 40-acre spacing, which is necessary for the geology in tight gas sands. This is not shale. This is Wyoming. This is closer. This is shale. This is the Barnett area. This is northwest of Dallas-Fort Worth. Dallas-Fort Worth is right here. The airport is right here. Cowboy Stadium is about right here, and there are gas wells being drilled under Cowboy Stadium right now by Jerry Jones. Those of you who are professional football, don't worry about him having enough money to pay his players. I never worry about Jerry Jones being broke. All right, this started out as 40-acre spacing, went up to 80-acre spacing as they were experimenting in the Barnett from the early 1990s to early in this century. They were exploring, and they were realizing they can go to longer laterals. Longer laterals means longer spacing between pads. Fewer pads, more wells per pad, bigger spacing. Okay? So this is closer to what's actually happening in Pennsylvania. Okay? The idea here is one pad, multiple wells, make sure the wells are going perpendicular to the major joint sets. So the geology tells you which direction to go. You always have some of the wells going one direction, the rest of the wells going the opposite direction. And the orientation of that is dictated by the orientation of the joints that are down there. And here are actual maps taken from applications for permits in New York State. So this again, Chesapeake Company asks the New York State DEC, your version of DEP, we want the right to declare this to be what's called a spacing unit. That's an area that is agreed upon by 3 parties. The operator, the gas operator, the New York State DEC, and the landowners who control 60% of the land in that area. In New York State, the law is currently, if you can get the people who own 60% of the land in a spacing unit, then that spacing unit can be agreed upon by the state and the operator as an area in which wells can be drilled. The other 40% of the people don't have to agree. That's called compulsory integration. It's written into the Bill of Rights. The Bill of Oil and Gas Rights. Anyway, so the idea here is they would put a pad right here, and in this case they wanted to drill 5 wells north-northwest, 5 wells south-southeast, and that's the way it would work. And if this were a situation where Chesapeake would control large areas and they had no competition, and 60% of the land was controlled by landowners who really wanted to work with that company, then they would put another spacing unit here, and another spacing unit here, and another one here, and it would look like that. That's the ideal. That's just like the Dallas-Fort Worth Airport. Each one of those red squares would be a pad, and we'd have wells going. This would be the area around New York, near where I live, where all the permits are for wells going north, northwest, south, southeast. Whether that's going to happen or not depends upon you, people who own the land. If they don't agree to that, then it can't happen. This is a recent study that you should all go read. It's done by the Nature Conservancy in collaboration with the state of Pennsylvania, DEP, and in collaboration with a large number of gas operators. They got everybody around the table and said, let's do our best at forecasting high, medium, and low. What might Pennsylvania look like in 30 years? So go read that report. It's online, publicly available. This is what they predict under medium development, 10,000 well pads in Pennsylvania in 20 years with an average of 6 wells per pad. Okay? That's what they call their medium scenario. The high scenario is a lot more wells and a lot more pads, but this is what the pad distribution would look like in southern Susquehanna County and northern Wyoming County. Each one of those would be a pad. Okay? So that's a prediction made by industry people working in collaboration with your DEP and the Nature Conservancy to try to give you a view of what things would look like. All right, what can go wrong? From above and from below. What can go wrong from below? Lots of myths here. Certainly, there's the possibility that gas, drilling fluid, and brine can migrate up through the well structure. By that I mean the casing and the cement. It's a human-made structure. It's imperfect. As you know, cement jobs can fail. They can be faulty to begin with. They can fail later on in life. Casing can corrode. Casing can burst if there happens to be a void in the cement job over a sufficiently long length of the casing. You're putting 10,000 psi of fluid pressure in a casing that's a 1/4 inch wall thickness, 6 inches diameter. That's 200,000 pounds per square inch. That bursts the casing. This can happen. Okay. So lots of things can happen from below along the well string. Shallow, medium, and deep. Dimick, relatively shallow. Within the first 2,000 or 3,000 feet, things badly went wrong with the drill string. Another possibility is that gas, frac fluid, and so-called produced water, the stuff that's down there now, or the stuff that's down there mixed with the fracturing fluid, could migrate literally up through the formations above it. Now, industry says that's impossible. And I say this, no good scientist or engineer would ever use the word impossible. It's improbable. It's probably highly improbable in any one well for that to happen. Because for that to happen, a number of really bad things have to simultaneously occur. And the probability that that set of bad things would line up is unlikely but not impossible. Witness BP in the Gulf. 5 or 6 things had to go wrong in the right order. It can happen. I don't lose sleep over this. This is not my main concern, this. It can happen. I'm not worried about it because it's improbable. If you got 120,000 wells in Pennsylvania, it might happen once or twice. The consequences could be severe. The consequences might be mild. So you get migration up the groundwater and a dozen families lose their groundwater. Or you get migration in the groundwater and it's an aquifer that's serving a whole community. So we don't know. Where are the models? The model I showed you from 1984 on the supercomputer, I've been scanning the SPE database recently. Who is doing modern supercomputer-based simulation of 5,000 feet of different layers of rock with different joint formations, with different joint properties, injecting fluid down here at 10,000 psi, 500,000 gallons at a time, and asking what's the probability that it can find its way up? The industry can do that. They could do it tomorrow. They probably have. That's what the EPA is trying to figure out right now with their ongoing study. We're going to have to do it ourselves, or hopefully some gas company is going to come up and say, or Schlumberger, I like Schlumberger, we already did it, here are the answers, here are the probabilities. They just tell us, we wouldn't have to do work again. And then we can put that one to bed as a low probability event. The things that can go wrong with cement jobs, this is from the Alberta Energy Utilities Board, again up in Canada. You've heard a lot of this from the Dimick situation. You can have migration along the contact between the cement and the rock. You can have migration along the contact between the cement and the casing. That's loss of bond. You can have diffusion of fluids through inaccurately made cement. You can have fracture of the cement that leads to debonding. You can have rupture of the casing. You can have the cement well plug, which is put in the well after the drilling but before the fracturing process to shut in the well. That plug can fail. These are all the things that can go wrong and have gone wrong in Alberta and British Columbia. That's why this picture was created, to warn companies that these are the things that can go wrong. We're going to be inspecting for these things, fix the problems. Back to British Columbia, safety advisory from earlier this year, communication during fracture stimulation. This is also stuff that can go wrong down below. And by communication here, they did not mean that Halliburton called Schlumberger. By communication here, they mean that during the drilling of one well, fracturing was occurring in a well that they thought was too far away to have any influence, and it wasn't. That's called communication. While you're drilling this well and fracturing this well, you don't want the 10,000 psi, 500,000 gallons of fracturing fluid that you're pumping in here to come out there. Could this happen? It has happened. 5 incidents of fracture stimulation resulting in communication with an adjacent well during drilling, 3 incidents of drilling into a hydraulic fracture formation during a previous stimulation on an adjacent well and containing high pressure fluids, 10 incidents of fracture stimulations communicating into adjacent producing wells, blah, 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 blah. Bottom line here is fracture propagation. Do you remember the article, the quote from the article that I co-wrote in 1987? It's very difficult to predict in a highly fractured formation what the fracturing effects are going to be. This is 2010. Fracture propagation by way of large-scale hydraulic fracturing operations has proven difficult to predict. Existing planes of weakness and target formations may result in fracture lengths that exceed initial design expectations. Surprise. Oops. Anybody see something wrong with this picture? Here's the drill rig. You can presume that the well is here. Old Faithful. It's a man-made geyser. This occurred last month in Texas. Yeah. Frac fluid and well, it's not only frac fluid, it's brine that's down there. I still haven't found the answer to the question I asked last week. I know this was going on for at least a week. And so the main problem here was this was a sour well. There was hydrogen sulfide gas. And so they had to evacuate an area and put people up in motels until they fixed this problem. The point I'm making here is that it is possible, if you have a large number of abandoned wells and you don't know where they are, and if you haven't done proper seismic investigation of the area that you're going to drill and frack, it is possible that you will drill into or frack into an area where there's a pre-existing abandoned well, which is a pipeline to the surface. And that's what happened here. So be careful. What might go wrong from above? This is what I'm concerned about. Okay? The farther up you come, the less you rely on Mother Nature for protection, and the more you rely on people for protection. When there's 5 or 10,000 feet of rock between you and what's down there, I feel a lot more comfortable than when there's just a driver with an 8,000 gallon truck of frac fluid. Okay, that's a human driving a human machine. Bad things can happen at higher rates. So spills, ruptures, seepage, drilling fluids, frac chemicals, flowback fluids, which people sometimes call produced water, go where they do not belong. Okay. This happens, in my opinion, too frequently in Pennsylvania. And we'll talk about frequency in a minute. There's always going to be airborne emissions. There's too much talk, I think, about water contamination. It's appropriate, but it's imbalanced because what's happening in these heavy industrialized areas with many wells per square mile and a pad every square mile is heavy industry. So you're going to have emissions. You're going to have emissions from all the equipment burning diesel. You're going to have VOC emissions from the flowback fluids, which are being usually put into open pits. Not always, but usually yet by most of the companies. Stuff just evaporates. How much water? You've heard all this. I'll skip right to the chase. You can go to the Chesapeake website. They're saying they're averaging 5.5 million gallons per well. I don't concern myself yet about how much water needs to be withdrawn from the Susquehanna or the Delaware or the Monongahela. I'm going to be very concerned when they come to Cayuga Lake. That's where I live. I was being sarcastic there, but that's a problem, getting enough water to do the frac jobs. We're lucky. We live in an area like British Columbia where there's usually plenty of water. But one always has to be mindful of where you're taking it from, that you're not having a detrimental environmental impact on what the animal life in that stream expects. What goes down the well? Lots of myths again. Myth, 596 separate chemicals are added to that witch's brew during hydraulic fracturing. False. Over the lifetime, over the history of hydraulic fracturing in the United States, at least 500 to 600 chemicals have been identified as having been used in one or more fracture jobs. That's different than saying in any one fracture job in Pennsylvania tomorrow, 596 chemicals will be used. That's not true. Well then, Professor, how many chemicals will be used? It depends. Depends on the company that's drilling the well and fracking it. Depends upon the geometry. It depends upon the geology. It depends upon what kind of fracking process they're using. Is it a traditional gel frac? Is it a gel plus foam frac? Is it a slick water frac? Is it a hybrid frac? Or any of the combination of the above? So for a slick water frac, these are the absolutely necessary chemicals. There has to be water. There has to be proppant, usually sand, but not always sand, something to hold the cracks open. There has to be a biocide to kill the bacteria. There has to be a fluid loss additive. There has to be an anti-corrosive. And of course, there has to be a friction reducer, otherwise you don't have slick water. And there has to be an acid. Those are bare minimum. So you can go on the, say, the Halliburton website that came up last week, where they're now saying we're not going to tell the EPA what we're using, but we're telling you, the American people. Sometimes I just don't understand public relations vice presidents at gas and oil companies. If they just did the simple thing, it would make it simple. So they tell EPA to stuff it, and then they come up with a website that says the American people can judge for themselves what kind of chemicals we're using. And so you can go to the Halliburton website tonight, and they'll tell you, here are the MSDSs for all the chemicals and all of the kind of frac jobs we do, which is fine. That's a step forward. But be careful, an MSDS doesn't tell you everything you need to know. Read the fine print on the MSDS, whether it's for the chemicals under your sink or the chemicals in your frac fluid. Having an MSDS doesn't say it's not hazardous. It just describes the hazards up to the point that the research has been done on them. And most MSDSs, where it says known hazards, blank. Hazardous material, known hazards, blank. Because of the hundreds or thousands of chemicals that we use in our everyday jobs in our homes around the country, not just in oil and gas. Very, very small percentage of those chemicals have ever been tested for the wide variety of bad things they can do to you. So I'm not warning you about oil and gas, I'm warning you about all this stuff in your environment. Be careful. And by the way, for anybody here work for Halliburton? Anybody here have a relative that works for Halliburton? I would like to do something with my right arm that my mother said I should never do in public. But if you go to the Halliburton site, And if you scroll down, they do a good job of saying, here are all the chemicals, here are the trade names, here are the CAS numbers, here are the MSDSs, and by the way, here are the other common uses of these materials. And that's good. It's nice to know that some of those chemicals are used in ice cream. It's really nice to know that hydrochloric acid is used in black olives. I got educated last night. I found out that there's hydrochloric acid in black olives. I learned that from the Halliburton website. See, that's just jerking my chain. So am I now supposed to be less fearful of black olives? Or more fearful of the hydrochloric acid used in the frac? I don't know what the point is. Obviously the point is they're using 50,000 gallons of hydrochloric acid in highly concentrated form, and it has to be brought by truck and stored on the site, and it's injected, and while it's injected, it's not diluted with 500 million gallons of water. It's injected as a slug of hydrochloric acid because it has to go down there and do a job, which is to dissolve all the crap in the perforations. So to tell me that it's also in black olives doesn't inform me. It irritates me. And I'm going to continue to eat black olives, the passion fruit of the Sicilians. Okay, what comes back up? Well, partly the stuff that you put down there, but not all of it. As you probably know by now, the Marcellus in northeastern Pennsylvania is sweet and dry. Lucky you. Imagine you were in southwestern Pennsylvania where it's wet and sour. Okay, sweet and dry means almost pipeline ready. A little bit of dehumidification and off it goes to market. But everything you pump down there doesn't come back up immediately. And here's another myth. I had a Chesapeake vice president tell me to my face, right to my face. I was here, he was here, I was here, and I said, so how much of this stuff comes back up? And he said 11.819%. Okay. I'm an engineering professor. The first thing we teach our students in the freshman year is significant figures. You can't possibly have a number like 11.819% describing the average amount of fluid that comes back from your jobs. Maybe you could say 11%, okay? But that's what happens when they put MBAs from Harvard out there in public to speak for oil and gas companies. All right? They sometimes preach technical nonsense. So, but here's the more important thing. Yes, it is important to know how much comes back up. Why? Because you got to properly dispose of it. Okay? So if you say only 11% comes back as flowback fluid, that means you only have to dispose of 11% of it. But what they don't tell you is that most of it comes back eventually. It has to. Over the life of the well, all wells continue to produce produced water or brine. So when does what comes back up the well stop being flowback fluid and start becoming produced water or brine? When they deem it to be so. The fluid does not know what it's called. I know, I asked it. Most gas companies declare at one point in time after the frac job, usually within a few weeks, that the well is ready for production. At that point, that stuff that's coming back up ceases being flowback fluid and is now produced water. And because it's produced water, not flowback fluid, different regulatory procedures are put into place. So that's a committee decision done in the boardrooms of companies. When do we declare our well in production? Because when we do, it's no longer flowback fluid, it's now produced water. And when you say something is produced water, it sounds to me like H2O. Or you might call it brine. Brine tanks? Well, yeah, it's briny. It's a solution of salts, but it also has heavy metals, naturally occurring radioactive materials, and probably BTEX in it. So what you call it is different than what it is. What it is what you test it to be. And if you don't have to test it, because you've now stopped calling it flowback fluid, you don't know what's in it. And so when you start spreading it on your roads, because it's brine, you might be spreading something else. When you take it to your public wastewater treatment plant, where it is now diluted 100 to 1, and passed through your wastewater treatment plant, and they haven't tested to see whether there's heavy metals or norm in it, and since you're publicly owned wastewater treatment plant can't remove heavy metals or norm, you're now pumping that stuff perhaps back into your environment because you haven't tested for it. Can we fix these problems? Yes. First, you have to become aware of them by proper education of what the words mean and by proper understanding of the technologies. Then you got to get the regulations in place. You got to know what to test for. You got to get the regulators in site to test them regularly so that everybody follows the rules. All right. When things got started 3 years ago in Pennsylvania, all the return fluids eventually went into an open lagoon or a large impoundment serving more than one pad. There has been a tendency recently for some companies, not all, to move to tank storage. That's good. The fluids go into the tank. Where do the gases go? Can't capture the gases. What comes back is not only liquid, it's gas. And that gas can't be stored in the tank. The fluids can, and they can settle out, and they can filter, and they can recycle, and they can reuse. That's all good. But that's relatively recent, and not all 74 companies are using best practices. So you're starting to tighten up your regulations. 19 new pages of regulations were approved for Pennsylvania, Article 78. That's good. Another 100 pages, and you'll be there. All right, getting to the end, because I know you want to go home. How safe is safe? I started off by saying everybody in this room wants to leave here with a better understanding of whether this could potentially hurt me or help me. I made the statement that all this industrial activity that's going to take place over the next few decades here cannot improve your health. Okay, that's off the table. It might hurt your health, it might hurt your environment, it might hurt your pocketbook, or it can enrich you. Right, you got to decide whether the risks are worth it. What is safe enough? Can gas companies produce from Pennsylvania Marcellus wells in a way that is sufficiently safe that it will not harm the environment or human health beyond an acceptable level, that will not change your pattern and style of life beyond an acceptable level, and will not cause undue economic harm beyond an acceptable level? If you know the answers to those questions, let me know. Those studies are now just starting to be done. Okay, so let's look at some of them. Professor Engelder, the guy that did the studies at Penn State that predicted how much gas and how many wells you have to drill, speaks frequently around Pennsylvania, up in New York, does the same thing I do, has a somewhat different perspective on things than I do, but that's okay. So he's encapsulated this whole problem of risk into a very narrow discussion. Too narrow for me, but I want to describe it to you. He says the major problem, the major impact on human health and the environment comes from what he calls the meth-mud problem. That's methane migration and mud intrusion into groundwater. Now he's probably right that that's the most common kinds of problems. These are the endemic kinds of problems. But that's not the only kind, but he wants to concentrate on those, so let's do that for a while because we can quantify the risks. He's actually tried to do that. So these are his slides, three slides, this one, and now this one. So he's done some research, and he concludes that there was a significant environmental impact in the state of Pennsylvania during drilling for Marcellus in the period January 2008 to August 2010, one time for every 150 wells drilled. Now, there's something good going on here. This is called quantifying risk. Uncertainty quantification. That's what engineers call it. You can't make rational decisions about cost-benefit analysis without having quantification of risk. What's the downside? If you know what the rate of the downside is, you associate a cost with that downside, and now you can start doing cost-benefit analysis. You see? Okay. So Professor Engelder has done us a service. He's done some research, and he doesn't want to talk about Dimick. That's off the table. I don't know why. He doesn't want to talk about Dimick. So he thinks there is a serious environmental impact one time for every 150 Marcellus wells. And then he goes on to say that that's a really good record. Well, I don't agree. I have the right to disagree. I'm an engineer, he's a scientist. He's a structural geologist. I'm a fracture mechanic engineer. So I know about risk and fractures and factors of safety and reliability estimates. So I'm going to try to show you why I think that that's a very bad record. He then goes on to say, these are his words, that your Pennsylvania DEP has a mission, and it's to provide the leadership to the industry to develop even better practices. Now, I'm trying to understand what he means by that, so help me here. Does that mean that the DEP should have the technology and the experts to develop the best practices for the most technologically advanced industry in the world? I don't think that's what he means, because obviously it's not the mission of the DEP to do research and development for the oil and gas industry. So what does he mean by DEP being leadership? I think what he means is they have to increase the fines. That's leadership, right? You would encourage the industry to develop better practices if you fine them higher. I think that's what he means. I don't know. What do you think he means? And now he challenges the industry. He wants to improve not one significant environmental impact for every 150 wells. He wants them to get to one for every 500 wells in 2 years. Okay, so run the numbers. 120,000 wells. Okay, that's 240 significant environmental impacts. Is that acceptable? You make the choice. Hey, you're citizens of Pennsylvania. I was just a football player once. Okay, you got to decide what's it going to cost the state of Pennsylvania to clean up 240 significant environmental impacts over 30 years. Maybe that's okay if his numbers are right. I say the challenge to the industry is to have one significant event every 50,000 wells. So I was giving a talk like this last week, and somebody jumped up, a guy who works for FEMA, and says, that's absurd. Professor Ingraffea, it's absurd. The industry could never do that. They can't see what's going on down there, so they can't inspect it, they can't maintain it, so things are going to go wrong. Okay, so I also work in the aerospace industry. All right, my undergraduate was aerospace, so half of my time has been working in rock mechanics down there, and the other half up there, aerospace. So there's a dictum in the aerospace industry. If you can't inspect it, you throw it out after its useful life is expended. Because if you can't maintain it, if you can't inspect it and maintain it, you shut it down and you start over again. So my response is, if the industry can't tell us that that well during its lifetime is going to maintain an acceptable level of safety, shut it in, shut it down, and drill another one. Keep them all young. That's what they do in aerospace. When you fly on a commercial jet aircraft, you're guaranteed there's a 1 in a million chance you're going to die on it. The federal law says that. I hope now you know that. You should feel safer. You get on a jet airplane, federal law says you have to be guaranteed by the people that manufactured that airplane and maintain it that the probability of your dying is 1 in a million. And it turns out to be about 1 in 10 million. Why? Because they can inspect most of it. But you can't inspect every square inch of every aircraft. So the critical parts that can't be inspected, they're periodically replaced in order to maintain the risk. Okay? One last example of why I think the current rate of accidents is unacceptably high. So I'm going to talk about what's called a communal industry. Common concept. A communal industry is one in which large segments of society participate, either voluntarily or involuntarily. Two classes of communal industries. I'm going to talk about one of each. So, a communal industry in which large segments of society voluntarily participate is getting on an airplane. You don't have to get on an airplane. You could take a bus, a train, or a car, or you could stay home. Or you can choose to drive across a bridge or not. Every time you cross a bridge, it's a voluntary participation in the bridge industry. You ever think of it that way? You're a participant in that industry. Somebody had to build the bridge, somebody has to inspect it, somebody has to maintain it. There are federal laws that say for every steel bridge in the United States longer than 20 feet in span, that bridge has to be inspected every 2 years. And if it's found to be cracked or corroded, it has to be repaired or replaced in order to maintain a minimum acceptable level of risk. So here's the level of risk. Over an estimated average 75-year lifespan of a steel bridge of over 20-foot span in the United States, It has to be shown through experience or calculation that the probability of your dying crossing that bridge is 2 chances in 100 million. That can be calculated out. That's what I teach my students to do when I teach them advanced fracture mechanics at Cornell. How you do that calculation. What do you have to design into the bridge to make it fatigue and fracture resistant so that those odds are achieved? And if it turns out during an inspection that there is bigger crack than you thought or more corrosion than you thought, then by federal law you are obligated to repair or replace in order to maintain that level. So, 2 in 100 million. Let's go to the other communal industry, the one that we've been talking about all night, in which you are being forced to participate. You're in Pennsylvania. You're already participating in it. You are participating in the unconventional natural gas industry. So what's an acceptable level of risk? I don't think the acceptable level of risk should be 2 chances in 100 million that you're going to have a blowout. That's asking for too much. This is a man-made system. An unconventional natural gas well is a partly man-made system. So let's do the numbers. This number means 99.999999% safe. That's the reliability index. 99 with 6 nines after it. So those of you who have thought about these things that think that 99.9 is almost virtually true, means 99.9 means there's 1 chance in 1,000 of something being bad. That's what 99.9 means. If you have 120,000 wells and you're 99.9% reliable, you got 120 failures. Is that okay? You decide. I don't think so. But let's take the extreme case, which I do not advocate, but just for the purposes of academic exercise. Let's suppose that we enforce that same level of engineering and technology reliability on the Marcellus gas play. And Professor Engelder estimates that there will be 400,000 wells over the entire Marcellus over 50 years. So how many major failures would we expect from 400,000 wells at that level of reliability? Fewer than 1. We already got by that. We're already at one for every 150 wells. That's 98.5% reliability. Now, if I were to ask you, is a grade of 98.5 good? You'd say, if my kids get it in high school, yeah. Right? If I was 98.5% certain that I was going to win the New York or Pennsylvania lottery, wow. See the big difference between 98.5 and 99.9? That's the difference between 1 in 1,000 and 1 in 150. When you have small numbers, that doesn't mean very much. But when you roll the dice 100,000 times, it means a lot. There's a big difference between 98.5 and 99.9 and 99.99 and 99.999. You got to make the call. What's an acceptable level of risk? To do that, you got to see the quantification of the things that can go wrong. We're just now beginning in Pennsylvania to be able to quantify the number of accidents per well, or the number of accidents per truck trip, or the number of accidents per million gallons of frac fluid. That stuff could have been modeled. We don't have to wait for the experience, your experience, to learn those things. They could have been predicted. Okay? And they can be predicted into the future, and people should be predicting them. That's half of the equation. Here is the probability of things going wrong. Assign a cost to them. Compare that to the benefit cost. Here's the expense cost. Here's the benefit cost. Weigh them. You decide. So, bottom line. Then we can all go home. And we have a lot farther to go home tonight than you do. When compared to conventional gas production, high-volume slick-water hydraulic fracturing from long laterals requires higher volumes of fracking fluids, produces higher volumes of liquid and solid waste, involves more spatially intense heavy industrial development, creates greater risk of accidents, spills, leakages, discharges, exposures to water and air. I hope to have proved that to you tonight by way of data, facts, engineering, science, and technology, and a couple of quips. But ultimately, you get to make the call. So thank you all for all this exorbitant amount of time. I appreciate your coming. Time for Q&A, but think, act, and if you want to get in touch with me and tell me I said something bad, wrong, irreverent, ignorant, let me know. I'd be glad to try to improve next time around. So thank you all, and I think it's time for Q&A.